So good afternoon. Good afternoon, Physics 20. Today we're going to continue on with our simple harmonic motion. Yesterday we looked at the equation for a period of a mass spring system, and we came up with this equation here, T equals 2 pi times the square root of m over k. So what we're going to do now is we're going to take a look at a pendulum, which is also exhibits simple harmonic motion. Just think of a swing, right? When you swing, you have an oscillation where you swing forward and then back to your original position. But a pendulum doesn't have a spring constant. So if you recall from yesterday, this was the equation that we derived for a mass spring system. And so if we want to use this equation here, we have to somehow eliminate m and k from this equation. So we're going to do that by taking a look at a pendulum or this diagram of the pendulum. And what we're going to find out later on is that the mass will not affect or is not affected by the period, or will not affect the period of your pendulum. So when we look at this equation, we want to try and get rid of the m and the k. And the way we're going to do that is we are going to look at our pendulum. We're going to take a look at a couple triangles. So the length of our string is L. So this is the length of the string that we suspend the mass from, or the bob is what they call it at the end. So this is the length of string. And we're going to measure that in meters. And if we take a look at this theta here, this is the amplitude that we're going to pull back or move the bob through. We can derive that if we take a look at this right angle triangle right here, as the sine of theta is equal to the opposite, which is our position, over the length of our string. So if you take a look down here, this purple arrow, that represents our position. So how far away from equilibrium. So this dotted line right here, this is where our x equals 0, and we are at equilibrium. So that's how we can solve for sine theta. Now, if you recall from our previous chapter, when we look at a pendulum, the restoring force is the force of gravity. But force of gravity is acting straight down. That's our F of G. So we are going to have to resolve that force of gravity into its two components. So if we resolve it into the perpendicular, we get that force there. And then if we move this way, this is going to be F of G in the parallel. And it is the F of G in the parallel that is actually our restoring force. Okay, so just remember now that our restoring force, Fr, is going to be this F of G parallel. Okay, and if we want to solve for F of G parallel, we're going to use the same angle here. That's the amplitude that we pulled back on the bob, or we pulled the bob through that angle. We're going to use that same angle, and again, this is a right angle triangle. So if I take a look at my F of G parallel, it's going to be F of G times the sine of theta. And then always remember, we can replace F of G is our mass times G. Okay, so this F of R is going to become, our restoring force is going to become F of G times the sine of theta. And so we can start doing some replacements here. So we know that from our equation over here that we can solve for sine of theta by looking at our position or displacement over the length of the string. So I can sub that in here first. Times x over L. And we also want to get rid of, so the whole goal here, remember, right, is that we have this equation for period on a mass spring system, and we need to eliminate K because we don't have a spring, right? This is a pendulum. So we're looking for a way to erase, or not to erase, to eliminate this K. So if we look at FR, we also know that FR, when we're looking at a spring system, is equivalent to the spring constant times the X. So this would be F of G times X over L. Okay, and I'm just going to bring this over here. So now we have K times X equals M times G times X over L. And remember, we're trying to get rid of K, so I want to solve for K. So now I'm going to divide both sides by X, and X is going to cancel on both sides of the equation. So now my K, my spring constant, is equal to my mass times gravity all over my length. So now I can take this equation here for K, and I can sub it in here for my spring constant. So now I can eliminate the spring constant. So let's bring this down here. This is now going to be T is equal to 2 pi times M, all divided by, right, M times G, all divided by L. So remember, when we divide by a fraction, we're multiplying by the reciprocal. So T is going to be 2 pi. This is going to be M times L over M times G. So again, if you need a reminder, we're saying M is being divided by M times G over L. So when we divide by that fraction, we're multiplying by the reciprocal. And that's how I eliminate my mass as well. And I end up with the equation T is equal to 2 pi times L over G. Take a look. Do we have to derive this equation, or is it found on your data sheet? And if you took a look, you will notice that this is on the data sheet. So you do not have to derive it. You can use it straight away. Okay. So let's take a look here, and let's just look at this equation now. So if we're doing this, if we're solving for the period of a pendulum, which is what we're doing here, this is for the period of a pendulum, you will notice that the time it takes for the pendulum bob to swing back and forth is only dependent on two things. It's dependent on the length of the string that the bob is hanging from. So this length of string here is going to determine your period, and gravity. So you need to remember then that a pendulum's period will be determined by gravity. And we talked about it earlier in the unit that gravity, or in the last unit, that G, little g, will vary with altitude and latitude. We normally say that G is 9.81 newtons per kilograms at the Earth's surface, and that's just kind of based on an average value that we calculate. And so we can actually take a pendulum, and if we know the length and we determine the period, or measure the period of that pendulum, we can then determine gravity, or G, at that location. So let's try that here. We're just going to take this equation here, T equals 2 pi over L over G, and we're now going to solve for little g, for the force of the acceleration due to gravity. So the first thing we're going to do is going to move over the 2 pi. So we're going to, here, let's write this. over here. So we're going to go T is equal to 2 pi times L over G. So first thing we do is move the 2 pi. So divide both sides by 2 pi. On the right, it's going to cancel. So now we're left with the square root of L over G is equal to T over 2 pi. We are now going to get rid of the square roots, so we're going to square both sides. So now that's going to become L over G is equal to the period squared over 4 pi squared. And now that G is in the bottom of the equation, I'm just going to flip both sides, so take the reciprocal of both sides. So this now becomes G over L is equal to T squared, sorry, I got to flip that, 4 pi squared over T squared. And remember, we can do that reciprocal because we don't have any addition or subtraction. And then just multiply both sides by L. And now I'm left with G is equal to 4 pi squared times L all over T squared. Okay. And so this equation we have to derive. It's not on our data sheet, so you may have to solve for G, but again, you're starting already from this original equation on this side, right? We're starting from this equation, so it's not a super hard equation or way to solve for G. And if you take a look at it, do we have an equation for acceleration that is similar to this? If you look at centripetal acceleration, we do. We have AC is equal to 4 pi squared times the radius over period squared. So the two are very similar, which makes sense because they're both talking about an acceleration. Okay, so when pendulum clocks are being made, they have to take into account the acceleration due to gravity at that location, because it may change the period of the clock, and if you don't have the right period, you will not keep proper time. Okay, so let's try one example, and then I'll leave you guys with the rest to do in class today. And the chapter assignment is open if you want to start looking at it, but maybe you should try some more of your practice problems that you missed yesterday. Okay, so let's try example 3, and then I'll let you do some work. What is the gravitational field strength at the top of Mount Everest at an altitude of 8,954 meters if a pendulum with a length of 1 meter has a period of 2.0 seconds? So we know the length is 1.00 meters. We know the period is 2.01 seconds. We also know the altitude, so we know the height is 8,954 meters, and they want us to solve for G. So take a look at your equations that we have, and you'll notice that we have T for a pendulum. The period of a pendulum is 2 pi times length over G. And so we don't really need to know the altitude for this. All we need to do is solve for our G. So you're going to isolate again for G. So you're going to divide both sides by 2 pi. So then we are left with, T over 2 pi is equal to the root of L over G. We're going to square both sides. So now it becomes L over G is equal to T squared over 4 pi squared. And then from there you can take the reciprocal. So it's going to be G over L is going to equal 4 pi squared over T squared. And that's because we took the reciprocal. And then we end up with our final equation. G is 4 pi squared over t squared times L. So multiply both sides by L. And again, you can show me as much work as you need in your equation, but you just always have to start with the original and then show me your final manipulated equation. So this is now going to become 4 pi squared times our length. This is 1.00 meters. All divided by our period, 2.01, and don't forget to square it. So G, if you solve for it, should be 9.7716 Newton per kilogram. If you said meters per second square, that would still be okay. But they are actually asking you for gravitational field strength, so newtons per kilogram makes more sense. And then we're going to round to 3 digits, so 9.77 newtons per kilogram. And that would be our final answer. Okay, so you'll notice at the bottom of your page here, you have the following practice problems to do. Okay, what I would like you guys to do is to read through 7.4. You don't have to make your own notes. We'll discuss those tomorrow. We'll discuss 7.4 tomorrow. But make sure that you do any practice problems that you're missing today. Okay, have a great afternoon.